In this video, we're going to talk about what it means to do a triple integral over a more general solid than a box. So let's just do a quick little recap of what we've seen about triple integrals. And so the triple integral over a solid S of a function f of x, y, z dv for volume, is the following, or can be interpreted in the following way. We talked about two kinds of interpretations. One, if the function f of x, y, z is a density function. Sometimes actually that density is written as rho of x, y, and z. So that is actually the more common notation for a density function, but we can call it f. So if that is a density function, for example, in grams per centimeter cubed, a function that gives the density at every point x, y, z in S, then the triple integral of the function dv over S represents the total mass of the object S. The second interpretation that we talked about is if f of x, y, z is the joint probability density function. Now, we haven't talked about that yet. That is something that is upcoming for us. We've talked a little bit about it. That's not true in our interpretation of double integrals, but we haven't done a deep dive into joint probability density functions yet. That is coming up. But if f of x is one of these things, the joint probability density function of three random variables x, y, z, and S is interpretable as some event, so these three variables x, y, z determine some event happening, and that event is determined, or that event is describable in terms of a solid S, then the triple integral represents the probability of that event, the probability of S. We also talked about the simple case. If S is a box, if it's a box B and a box B is given as a cross product of intervals, AB cross CD cross EF, the triple integral can be calculated as an iterated integral in any of the six orders, right? So the triple integral over S, which is the same thing as the triple integral over B if S is a box, is an iterated integral. So the integral from A to B, of the integral from C to D, of the integral from E to f of x, y, z, and then we have to put these in the correct order, dz, dy, dx, and then the iterated integral, just like for double integrals, can be split in or evaluated in any order. And so here's another order written right here, and there are 6 of them total, right? So I haven't written them all, but there's more orders for a box. So what happens if you want to extend this idea of a triple integral to a more general solid, right? So not all solids are boxes, just like not all planar regions are rectangles. So what do you do, right? So with the rectangle, right, we were able to extend it to a general region. Now we're going to extend to a general shape or a general solid. And so what we have to do is classify, like we did with our regions. We're going to classify these solids by type, according to their boundary, according to their boundaries, to know how to proceed. And so in planar regions, there were 2 types. In solids, in general solids, there are typically 3 types of solids, and then the integral is set up slightly differently depending on each of those types. So what are the types of solids in R3? So we'll take a look first. This numbering, type 1, type 2, type 3, I mean, it really doesn't matter what they're all called, as long as we recognize what's important, and that's the geometry of them. So the geometry of a type 1 is a solid that is bounded above and below, bounded above and below. right? So it's bounded above by a function z, which is a function of x and y, u2 of x and y, and then it is bounded below by another function z in terms of x and y. And so what we do for a triple integral in that case is we start out by writing the single integral, a single integral with respect to z, y, because the boundaries are given in terms of z equals, right? Z equals, those are z values above and below, right? So that's here the triple integral of our function dz. And what happens to z? Z goes from, right, if I'm going to write this as an inequality, u1 of x and y is less than or equal to z is less than or equal to u2 of x and y. And therefore, our first integral goes from u1 to u2, following exactly the same order of that inequality. And what is left, therefore, on the outside is a double integral, So this double integral here over d, dA, well, d is the shadow. So we already talked about shadows when we talked about an application of double integrals. D is that region on the xy plane, for type 1. D is that region, the shadow of our solid. And so what does that mean? D, then this integral has to be evaluated as a double integral. So once we do our step 1, right, once we do step 1, the step 1 was the inner integral of the triple integrals. Then step 2, well, step 2 is just reverting to what we've done before. Once you've got that step 1 done, this is going to be some answer, right? You'll have some answer here. The z is going to be gone. Why is it gone? Because you will have integrated it away. You'll have integrated away. So your answer here will just be a function in x and y, and then you'll be left with the double integral of your answer, right? You'll be left with the double integral over d of whatever you got out of the first integral, the answer of x and y dA, and then it becomes an old problem, right? So once we get that first step in, the second step is just a regular old double integral, right, that you've done quite a bit of so far. So that's a type 1. Type 1 is bounded above and below. So type 2. Type 2, and you might see these numbered differently. You might see them numbered differently in different books or whatever. I don't care. I'm never going to ask you, what is a type 2 integral? Right? I don't care about the numbering. What I care about is that you recognize the properties of each of them. And a type 2, the way I've numbered them here, is bounded. It's bounded not above and below, but it's bounded front and back. So it's got an easy front boundary. Here's our front boundary. X is v2. And if x is written here, if x is the dependent variable, then it is dependent on the z and the y inputs, right? So it's dependent on the z and the y plane. And so you're going to see here this region D that we're going to talk about in a moment is in the YZ plane, is where the region D ends up with that. So we have this front function, we have this back function, and so if we were going to create an inequality for x now, well, it would be the back is the lower value, v1 of yz is less than or equal to x is less than or equal to v2 of yz. And so we do the exact same thing. We create an inner integral. That inner integral is now in terms of x. So it is x that is going from v1 to v2, right? X is going from v1 to v2. So that inner integral is going to give you an answer. And your answer then is going to have no more x in it because the x will have disappeared when you do FTC2, right? You're going to plug in x is equal to v2 and x is equal to v1, which means that you're going to have an answer now in terms of y and z. And then your second step, right, so that's your first step. Your second step is going to be a double integral. So your double integral now over this region D, which is a region in the YZ plane now. And that's going to be a double integral in Y and Z. And so you can do that in any of the ways that you learned before. And so what were those ways? You could do that as a type 1 D region. You could do that as a type 2 D region if D ends up by being circular. You might do D as a polar integral afterwards, right? Anything is possible. Once you've got that inner integral done, then the outer integral becomes like an outer double integral, I could say, is like a brand new problem. It's like something I could have given you 2 weeks ago or whatever, right? It's just a double integral that you yourself have created after integrating the first inner integral. The double integral is then like a fresh brand new problem. So then the last type that we have is a type 3. So we have above and below, that was type 1. We had front and back, that was type 2. And the way that I have these numbered here, this type of region is a region that is bounded right and left. So here's a function which is the right bound of our solid. Y is equal to w2 of x and z. Here is our function which is the left bound. And so if y is the dependent variable, then the independent variables are x and z. And so the input region, or the shadow region, is going to be in the xz plane this time. It's going to be in the xz plane. And then you do exactly the analogous operations. You know that w1 of x and z is less than or equal to, the y value is less than or equal to w2 of x and z, which helps you set up your integral, right? You're going to do, again, an inner integral. That inner integral is with respect to y first. And then those y values are going to go from the lower y value, which is a function, right, from w1 up to w2 of x and z. You're going to integrate out the y. So this time your answer is going to be a function of x and z. And so when you do that remaining double integral, the double integral of the answer, it's going to be a function of x and z dA. And again, you can do that in type 1 region for D, type 2, polar, whatever techniques that we had learned before for double integrals applies now. So I should mention that, oh, well, this is what I've already mentioned. Haha, look at that. So then each of these double integrals can be expressed in 2 orders, right? Type 1, type 2, that's discounting polar. And so depending on whether D is expressed as a type 1 or type 2 region, right, if we do each of 2 types, right, type 1 and type 2 regions for each of the 3 types of integrals, right, so there's 3 types of solids, and for each of those we are going to have to do a region D, and there's 2 types of regions, then totally, or in total, we are talking about 6 possible orders of integration. And so just like we did with double integrals, where I might give you 1 order of integration, a higher level problem is going to be to give you an integral and ask you to reverse, not reverse, that would mean there's only two orders, but to change the order of integration into a different order. That's quite a complicated problem, typically requires some visualization. So we're going to practice just evaluating these integrals first, setting them up, and then eventually we're going to change the order of integration, which is going to be a bit of a challenge.